Can someone give me a sound check?
What you have to offer.
I can hear you, but it's Scott.
Okay, thanks, Scott. And thanks for resending that link.
Yeah, as you can see, I'm trying to show the entire picture,
Most helpful.
Right.
which
Okay.
honestly I have found nobody has done. Everybody keeps talking about it,
Right.
but I haven't found anybody yet that has in one spot shown the entire picture.
Right.
So I think I have most of it.
Okay, I'm going to step away for just a minute here just to stretch my legs, and I'll be right back.
Sounds good.
Hey, Jack, how you doing?
I'm good. How are you?
I'm good. How's my sound?
It's fantastic. Am I coming through well?
Yes, you are.
Awesome.
Yeah. Yeah, I had some VPN issues there when I was trying to download something a few minutes ago. So hopefully, I disconnected my VPN. That's usually the culprit.
Yeah, I'm currently I've got all my siblings. I asked them to turn their Wi-Fi off just so I didn't no issues.
So are you on break from school now, college?
Yeah, so we finished up last week. We had our finals and now we're kind of on a 1 week break until our summer semester starts.
I see. Yeah, I brought my son home from college last week, so yeah.
Is he doing summer school or interning, or does he get to be home all summer?
He's taking classes.
Okay, yeah.
All I can say is boiler up,
Yes, boiler up, hammer down.
2-time graduate self.
Awesome.
Was that Phil? Phil Balin?
No, Bill Schubert.
Oh, okay. Okay, we got 2 minutes here. Let's see. Is that right? 2 minutes? Let's see. Yes. And if I remember correctly, this is a pretty short presentation, Jack.
Yeah.
Okay.
It's not too long.
Yeah, we're in the 15-minute blocks now, so it's kind of rapid fire. Okay. Is John Fleming on? He's the next speaker. I don't see John Fleming. Well. So, Jack, I'm going to turn my camera off after I introduce you. Then I'll put it back on 2 minutes when you still have 2 minutes left to just kind of give you a heads up that you're coming close to the end of your block there. So just a heads up on that.
Awesome. Thank you.
$70, $75, $77. Okay, we are at 3:15 East Coast time. So we'll go ahead and get started with the last block of the meeting here. And our first speaker is Jack Gill from Purdue University, and he's going to be speaking today about ground fuel discovery. This is a follow-up from an earlier presentation that he did. Jack, the floor is yours, and I'll go ahead and advance your slides for you.
Awesome. Thank you so much, Everett. So as he introduced, my name is Jack Gill. The other three members of my team who should be lurking somewhere around here in this chat are Christian Washburn, Ram Prabhu, and Haofei Tien. Together, us four, we are all electrical engineers in our first year of a special type of master's program called the Project Track at Purdue University. And as Everett mentioned, this is the end of our prototype phase for our project. Next slide, please. So here's an overview of the idea for our biofuels discovery package. The idea is that given any type of LiDAR data, our software will have two main algorithms to provide both canopy and ground fuels. So the way it works is first we take in the LiDAR data and then move to our canopy fuel algorithm, which develops both a canopy height model and then gives out the canopy fuels. And then from those derived canopy fuels, we produce a ground fuel, or we apply our ground fuels algorithm and show the predicted ground fuels in a report format. So the reason this works really well is because LiDAR has great spatial sensitivity, especially when it comes to looking for things like DBH, which is that diameter at breast height of a tree, as well as the base crown height and the canopy crown height. From these characteristics, we found that when machine learning is applied, we can find and determine other fuel characteristics both in the canopy and in the ground. The next slide, please. So here are our technical results. So as you can see here in the green were our initial goals set in January, and then in the red we have what we achieved. So it's kind of a poorly kept secret in machine learning that quality and quantity of data are much more important usually than the actual model provided. That's been emphasized earlier, that the more data you have, really the better model you can create. You can see that was kind of one of the biggest characteristics for our training, was how many samples did we actually have. The samples we got were derived from the Castle and Ikes fires in 2019 and 2020 respectively. These were in the North Kaibab area of Arizona. I think only about actually 100 miles north of where the current fires are in Flagstaff, Arizona. So they're fairly recent, and they were all LiDAR dated, or all LiDAR data. So as you can see, we actually managed to achieve fairly high accuracies, especially in that ground fuel algorithm, despite having a low amount of plot points. A lot of this was due to our optimization and just trying a whole number of different machine learning models to see what would work best for our given specifications and inputs and outputs. All right, and then another thing to point out that some of you may have noticed that with our product, it goes canopy fuels, and then the ground fuels is collected from there. So you might be wondering, how do we have a higher regression accuracy for our ground fuel algorithm than our canopy fuel algorithm? The reason for this is that, and I'll show this in the next slide, that our ground fuel algorithm was calculated off these Excel gathered points as opposed to, yes, thank you, Everett, as collected from and trained off ground plot data as opposed to trained off the outputs of our canopy fuel model. So you can see right here, here is how we actually went about training our data. So in the North Kaibab area, both canopy plot data and ground plot data were collected. There are about 700 plots we were given. And the ground plot data was collected using Brown's TFRSAC model. So there were 50-meter circles, or on the ground, where you were given a ground transect, and then 8 to 10 of the trees were recorded in the area. We were given things like species, crown type, and whether it was dead or alive for the tree. And then for the ground fuels, along that transect, we were given the duff, the litter, as well as the ground fuels 1 through 1,000 hours. Next slide, please. All right, so this is our an output of what our prototype beta software looks before you've selected a LiDAR. Each plot input is an 1,000 meter by 1,000 meter plot. And from there, you can take that LiDAR and you could select a given parameter as well as how you'd like to view the image. This is only relevant for the CFA, but for our GFA, you just select the parameter. Next slide, please. And so this is really exciting to show you guys. So you can see right here, we've got a LiDAR plot on the left. Once after we apply our software, we determine both canopy height and canopy base height. DBH is also calculated, but for the sake of a slide, this is all we'll show. As you can see in that we've got both a 3D model as well as a heat map. We ended up choosing heat maps for showing this data because we believe that's just a really succinct way to see the fuels or characteristics of a given area. So you can see on the right here, fairly directly correlated, you've got canopy crown height as well as canopy base height, and the values are in meters. And then next slide, please. Right. So this is really cool. So from our LiDAR image, or from our LiDAR derived parameters, now we're able to really apply this machine learning and determine, okay, what's actually going on down on the ground. So we have right down here a breakdown of some of the characteristics for our canopy fuel algorithms of what we actually calculated. So we looked at species, small branch weight, whether the tree was dead or alive, the fuel weight, and the crown type. So we had varying accuracies. I won't go all the way back to the technical results slides, but we are usually between 70 and 75% accurate for these parameters. And then also I'd like to point out, just for example, on the next slide, notice how in this dead live, you'll see in the top right, there is a large majority of dead. And so when we move on to look at these ground fuel parameters, you can see, already a correlation. You've got this litter in the top right. On the top right of the litter image, you've got less litter because it's dead trees. So dead trees aren't going to really be dropping much litter or duff. So that's a pretty cool correlation you can just see from looking at these images. So that's why in our software we have it so you can see both canopy fuel on top and ground fuel on bottom. And I'd also like to point out that our fuel weights are listed in kilograms per meter squared. Just for anyone, if they were wondering, based on our scales on the right, the gradients. And then finally, that last slide, please. Thank you. All right, so our future plans. We've been working fairly closely with Andy Hudak and Ben Bright of the Forest Service. I think a lot of you guys know those guys. They're really great. They've been super helpful. We're currently taking our prototypes, what I just showed you, and kind of turning it into a plug and play beta software that we'll be providing to them for all their help they've given us. And then moving forward, we'll be applying for, or we are in the process of getting intellectual property and copyright, so we can start, distributing this software to other branches of the government. And we'd also like to reach out to other Forest Service and other countries so we can really expand this data set. Like I mentioned, 700 plots really isn't that much. So the more data we have, the better models we can train and generate for higher accuracy. We'll be pursuing SBIR grants in order to continue this work. All 4 of us will be done with our masters either at the end of this summer or in the following or this December. And then finally, we'd like to move from a beta to a full product. So some of the ways we'd like to do this is we'd like to leverage the FIA data sets. Since those are classified, our plan is to provide our product to Andy Hudak so that he can run it. And then we can see, okay, now that you have 10,000 plots, how well are the models going to work? How useful can this be? And then we'd also like to broaden the ecological scope. So as we've seen with some of the other agencies, it's good to know the fuel, but you also need to know the fuel, or how much of a hazard these fuels play. So as we saw earlier with Richard McCrate's Firewatch, they not only have, what's the hazard posed by these fuels, but like where they are as well. So we'd like to pivot our data to be able to provide that as well. We'd also like to have a smoother interface, which includes more data streams. So like a lot of people have mentioned, a lot of groups here are using multispectral and hyperspectral data. We'd like to provide that, or at least fuse this data. So if people have LiDAR for an area as well as hyperspectral or multispectral, how can we get those to work together so that firefighters on the ground have a better idea of, okay, what fuels are in the area and how can we solve a fire or stop a fire if it's to come in an area. And then probably the most exciting thing we'd like to do is this idea of transfer learning. So just to give kind of a brief overview of transfer learning, this idea would be that data gathering can be super expensive, especially when it comes to developing ground truth. So the idea would be that we develop a model using, you know, the 10,000 FIA plots. And then there's ways to structural neural nets so that we could go to a group that, let's say they only have 10 plots or 100 plots, and they can simply clip on that data to the end of our neural net and still have that enhanced accuracy of, you know, 10,000 plots, despite only them themselves having gathered the ground truth for 10 to 100 plots. All right, next slide, please. So included on here, if everyone wants to access slides on their own time, we have a demo video just kind of walking through the software as a whole, just for everyone to see, you know, how it works step by step. And then finally, our last wrap-up slide. So we really appreciate the opportunity to be here. You know, as students this was a super cool opportunity. You know, Purdue lets us have all this IP, so we plan on just taking it and running, and we hope to be a part of the solution for forest fires. So as I said before, my name's Jack Gill, and then I have my other team members and their emails listed. Kind of some last big points for our software. This whole idea with this software is that it's a proactive approach. The idea would be that, you know, as LiDAR continues to be more and more widespread and gathered more across the United States, you could simply run this software in the LiDAR and get a great idea of, okay, what fuels are in an area, as well as the classification. It really will take advantage of the huge amount of data that's, you know, as we see more and more. I think someone was saying 100 planes are flown a day, you know, even if only a fraction of those are LiDAR based. This is super easy to apply to any, you know, .laz or .las file. And then finally, as Everett's mentioned before, this kind of software. So one analyst can run this software, and with those heat maps can really get a good feel for, okay, you know, you can look at 1,000 by 1,000 meter plots at a time, as opposed to, you know, reading through an Excel document, or even looking at a LiDAR point cloud, which is pretty indecipherable. So please feel free to reach out to us. We're 4 electrical engineers looking to help, and we'd love to. Thank you so much.
Thanks, Jack. I'm really excited about this for a number of different reasons. You say that you and your team are all electrical engineers. I think you really, you know, you did forestry pretty proud here with the work that you guys did, and it shows your understanding of, you know, how fuels are collected and so forth. And I'll attribute that to your connection to Andy Hudak, who I see is online here, and I'll thank Andy in advance for mentoring you guys. And who was the other fellow you mentioned? The last name was Bright.
Yeah, Ben Bright.
Ben Bright. Okay, I wanted to make a note of that because I wanted to thank both Andy and Ben. And Marva Willie has a couple comments here. She says, does your ground fuel model consider live fuels in the understory, or is it strictly for ground fuels in duff layer? And I think Andy actually answered that. He says no live fuels, at least not yet. No live fuels, at least not yet. And then Marva also says, thank you for your work in fuels inventory. Fuels management is an important part of both the fire management portfolio, but also the land management portfolio. We are always looking for innovations that will help us make better decisions as we address fuel management issues, but I still like doing browns. So yeah, I was really excited to see this. I've been doing a lot of discussion lately in a number of different venues about getting people interested in the science part of mapping and remote sensing and geodesy and things like that. And I know that Purdue used to have a really strong geodesy program. I don't know if they still do, but are there any other questions for Jack? I think we're probably right about at time for this time slot. But maybe Jack, if you and your team members could monitor the chat there, we'll go ahead and move on to the next presentation. So thanks again, Jack. There's John. Great.
Thank you so much. I really appreciate it.
Oh, you bet. Okay, John, there we go. So John, you have 15 minutes. I'll disappear here and then come back online to give you a visual cue when you have 2 minutes left. So And I'll advance your slides. So go
right.
ahead. The floor is yours.
All right, thank you. I really appreciate this opportunity to talk to you a little bit about what we did on the CHIRP program and how this might lend itself to help folks out. My first attendance at one of your sessions here. I'm a solution architect at Leidos, which basically means I get to look at all the cool new technologies and see if I can find applications that help solve some challenging problems. And along the way, I became the mission director for the one of our space-based systems called CHIRP, which was flown in 2011 to 2013. And through that, and in the years since then, I've been asked a lot about what we learned on CHIRP to various missions and different applications. And one of them that keeps coming up is wildfires and wildfire detection. So just a few thoughts in these slides on kind of a high level of where that world is going, what's out there, and how this might give you some ideas on how to use this technology going forward. So next slide, please. Next slide, if you have it there.
Yeah, there seems to be a little bit of a lag. It should be up now.
All right, I can talk through lags. Let me know if you're seeing the next slide. I can.
Yeah, it's is anyone else seeing the second? You got it?
Looks like I'm seeing it now. Yep.
Okay, great.
All right. Okay, I'm still seeing the old slide here.
Okay, just hang on just one second. I must stop sharing and then reshare.
Oh, there we go. No, I just saw it there at the end. Of course.
Okay, here we go.
I can talk fast too if you need me to. I've been told I talk too fast. There we go. The mission I come from, the terminology we often use, and if you haven't heard it before, we call these systems overhead persistent infrared sensors, or OPIR. At one point in time, they were called ONIR, for overhead non-imaging systems, which I think is an interesting concept because we usually think of the space-based imaging systems for nice, pretty pictures, good videos, and things. And these systems are designed in the non-imaging world. I mean, we're looking more for temporal changes and things that are changing in time domain primarily, that may have some spatial or spectral content to them, but to the most part, it's the temporal signatures that we're interested in. And historically, these have supported the U.S. military in missile warning and missile defense. These have been flown since the 1970s. Generally, scanning systems, the technology did not really support going much beyond scanning systems until the recent years, and that's kind of led to some advances. I'll talk about just a second. But the data has been fairly restricted. I know you had your DoD IC guys yesterday talking about what they're doing and stuff, and that does hamper us a little bit in sharing what all we've done on a lot of these programs. But there's certainly been a lot of interest and attempts to use these systems in a secondary role, or as we call it, the day job, of doing civil and environmental support missions and other things that we can do with them, because that's certainly a great use of these assets. And I certainly applaud those who are taking advantage of these existing systems that are out there. What we've seen in the last 10 years, though, is a real shift, a paradigm shift in this mission area in overhead persistent infrared, where scanning systems and systems designed in the 70s, 80s, 90s, and still being flown today have very generally scanning system technologies, and CHIRP and others have kind of started a new mindset in this technology area. As I mentioned, CHIRP, we launched in 2011. We actually powered off in 2013, completely healthy after a couple of years of operations. We did everything the Air Force set us out to do, and we moved on to newer things. But a lot was learned in that period of time, and that data has provided people an opportunity to better understand and assess the possibility of what can be done here. But the technology is not sat stagnant. Large formatted focal plane arrays, and I'm really talking things that are in the 2K by 2K, 4K by 4K, and even getting bigger, 6K, 8K type focal plane arrays are becoming more and more mature as we go forward, and they're more and more available, both for DoD and non-DoD missions. The focal planes we flew were actually designed for the James Webb Telescope. So you can tell there's a lot of cross technology and maturation going on. And as these new focal plane arrays, which have a lot of sensitivity in the infrared region and cover large areas, They continue to mature, they get cheaper, they get more available, and they certainly offer a lot more potential for other missions, such as detecting wildfires. The other innovation that really came out of CHIRP that I thought was worth noting is the idea of hosting payloads on other spacecraft. You can see a picture of CHIRP over there on the right, and I'll talk about just a second what we did. But up until CHIRP program, people were thinking about posting your payload on somebody else's satellite, and now that's kind of become second nature. We do a lot of that. NASA has looked at that. NOAA and has considered it. We do it in the DoD community. It's become a consideration, and there are pros and cons. I'll definitely be the first to state that, but it does provide an opportunity sometimes for a lower cost point to access space in different ways, shape, and form. And CHIRP kind of led the way with a lot of that. There were a lot of hosted payload symposiums that came about after that kind of got things rolling. But the community as a whole, though, is shifting. We primarily did these systems in geosynchronous orbit with fairly narrow field of view or moderate field of view systems, and there's been a lot of shift now. The optics and with these focal planes are varying a lot. They're narrow, medium, wide field of view systems. Some that go horizon, that nature, and the orbits are changing too. The geosynchronous orbit is not the only place we're deploying these. They're bringing them down to the medium Earth orbits, and there's a lot of work going on down in LEO. With constellations of satellites using these technologies, and the folks here may actually, if you haven't already, get a chance to go talk to the Space Development Agency and the exciting work they're doing with their space tracking layer systems. Those are done in LEO, and they may have great value for the wildfire community. But the last change I make that's really been a big paradigm shift, I think, is that because of systems like what SDA is doing and these other technological changes, there's a lot more suppliers out there too. There's a lot more folks who can build these sensors, as opposed to 20 years ago, you had one or two companies you could go to. There are a lot of folks who can do this now. There's a lot of increase in production capabilities. It's led to shorter development times. It's lower cost, which used to be a big problem with these systems, trying to get them up into space, and it gives you a lot more flexibility. So OPIR is no longer your mother's OPIR. It's changed a lot in the last 10 years, and it will continue to evolve and continue to provide opportunities. So when I talk about the lessons learned from CHIRP, if you'd asked me 10 years ago what lessons learned, my perspective, it's very different than what I will say today, just because of those technology maturations. So next slide, please.
Let me know if that comes through.
It's coming through. This will be a quick one. I just wanted those of you, probably 99.9% of you out there, I think 2 of you probably know what I'm talking about when I talk about CHIRP. CHIRP, a payload over on the left there is actually a prototype payload my company built. We built this for the Air Force, started out of the Air Force Research Lab, and then transitioned over to the what is now the Space Force. The time it was still the Air Force. And it was really a demonstration system to look for how we can use staring sensors to do the job that scanning systems had done before. And we built the system. You can see in the middle there, it is hosted. That's a commercial communications satellite. At the time, it was Orbital Sciences, now part of Northrop Grumman. Their satellite, this was built for the commercial communications satellite SES. And they had a ride. They had the satellite, and we had a payload. And we all got to talking and realized there was enough room on their nadir-facing deck, as you see on the top, to host our payload. And that provided a great opportunity to get us a ride up to GEO. And they were going there anyway, so they covered the launch. They had a satellite, and even better, they provided communications for us. We just hooked ourselves into their comm system. They gave us power. They did the station keeping. They provided the ground station. We just turned on our camera. They pumped our data down and routed over to my guys who are on the far right there, where we analyzed the data, and we looked at it, and we processed it for many years, looking at it with really COTS products, COTS networks, terrestrial comm from Verizon. I think we're using the link. So it was a very interesting approach to doing something, and getting commercial space involved with the DoD space to do something new and to fly it fairly quickly. So it demonstrated a lot of different things, and it kind of woke up a lot of people's eyes to what the potential was here of a staring large formatted focal plane array from GEO and what you could do. So a lot of missions looked at it. So next slide, I'll now highlight some of the high level conclusions. If you've ever had a chance to sit through one of my chats in the more secure environment, I show a lot of the data from CHIRP and what we did. I'm not able to do that here, but I'll say at a high level, what we demonstrated was clearly that a geosynchronous-based steering system gives you what, our terminology is persistent coverage, which means I'm basically steering all the time. Unlike a LEO system or a scanning system or a queued system, like maybe GOES, where you have to task the system to look area. We looked there all the time. We were on 24/7, 365. We were taking data. And, that generates a lot of data, but it's you never miss anything. You're always on, you're always looking, you're always doing something. And that's really a benefit from those wide field of view optics and those larger focal plane arrays that are available. What we also saw was that we could detect wildfires automatically. We could see them and detect them and flag them based on their temporal characteristics, on the change of the signatures we were seeing. And we did use spectral information to kind of augment that information. We had a filter wheel. We had 4 different bands, the ones in 3.9 microns and the 3 micron-ish type region proved very valuable in providing us additional spectral information. But it was those temporal characteristics that were very beneficial. And the temporal signals I'm talking about are much higher than, say, the 30 hertz rates you're talking about with GOES or the Fuego team was talking about earlier. We're talking temporal frame rates on the order of a hertz or even faster, maybe 30 hertz detection capability that provides you more hits early, allowing you earlier detection. So if you're interested in rapid detection during the early ignition stages, a high frame rate system offers you more opportunities to see it. And the characteristics of the fingerprints of those fires were actually fairly straightforward. No two fires looked the same, but just visually watching them, fires look different than other things we were looking at. And that temporal characteristic we leveraged for some automated algorithms. I'm sure folks a lot smarter than me could come up with some really creative ways of doing it. But I just encourage you to, when you think about the application of these sensing systems from space, it's not always about spatial or spectral information. That time domain can provide you some very unique stuff, and the ability to get high frame rate data and process it is a new enabler, not just by those focal planes, but also by the ability to have onboard processors. So that's been really powerful. Geolocation accuracy is really the challenge. You're a long way away. You can do some centroiding techniques, things of that nature to get it down, but that's really the challenge, and that's where I think the innovations are coming. A lot of steering sensor technology have matured, and I think that's where you can get some of that improvement in geolocation. You're never going to have that super high imaging system for spatial processing that you may like, but I think the temporal characteristics may provide you a different way to look at that same problem. And then last thought, just hosting is something I think you should always think about. It may not always be the right answer for your problem, but it can provide a reduced entry level cost to get you in there and get you in the game. You just got to find the right partner. And there are some partners like SCS, for example, who we work with, who do have rides coming up in the next few years and could host payloads of this nature. So one more slide, and I'll kind of give you kind of where my thoughts were at on if I was king for a day, what I would do next. And I would really focus on leveraging those new focal plane technologies that are out there. I think you can use geosynchronous systems to support your architecture. You understand the architecture better than me. That's not my job to tell you how to do your job. I just like you to be aware of the technologies and the potential that's out there. And what I saw, the benefits of these systems, they can help with early detection of wildfires, certainly in remote ones. I think it was the Cal Fires folks yesterday who talked about, they get plenty of detection. There are a lot of people around. What we saw was where we could fit in the niche role was where there weren't people in very remote areas, whether up in Canada or over in the Northwest US and more remote regions. We found that there were opportunities there to detect things that maybe didn't have the populations that were out there. So that was kind of the niche we were thinking about for systems. I think the shortwave, midwave spectral region is pretty good. In my vernacular, that's 2 to 5 microns. I think there are some window bands there that can be leveraged with those temporal signatures that may be of value for wildfires. And I think you can get reporting latencies down very short if you take advantage of onboard processing. Don't try and push all the data to the ground and process it on the ground. We're getting ready to fly space-based GPUs. So you can do a lot more on board than you might think, certainly you could have done 10 years ago. So there's an opportunity to do the processing on board, have direct downlinks right to first responders in the field, or a centralized clearinghouse where you can take a look at the information without having to have a warehouse full of computers and large bandwidth. So put me in a corner, what would I fly? Interesting enough, not that different than what some of the Fuego folks were talking about earlier. You know, about a 3 degree by 3 degree system from GEO covers most of Western US. We were a 9 degree system on Chirp, which is too big for what you need here. We covered a lot of stuff you wouldn't care about. You're not going to worry about fires in the ocean. But using a 3 degree by 3 degree with a 4K by 4K focal plane, which, by the way, we're flying 4K by 4K focal planes this year in space. So that technology is right there. You put those two together, you do simple math, and you find out you get about the 450 meter resolution that I think the Fuego folks cited, and I would say the same thing here. But what you have to keep in mind with these temporal systems, and you design them well, you can centroid on that information, same way astronomers do that centroiding, and you can get sub-pixel accuracy, half a pixel, third of a pixel geolocation accuracy, so a 450 meter sample size. With that centroiding technique on that temporal signal, you can get that down to probably on the order of maybe 150, 200 meter location with enough sensitivity. So that combination of processing with these technologies, I think, can certainly give you a possible solution in the future. And as I mentioned earlier, I'm thinking about the onboard GPUs, do that on board. We're doing that today for SDA. We're flying some pretty sophisticated algorithms on board. And you could really reduce the latencies, not be so dependent on large bandwidths, which are expensive, and certainly provide a very powerful system that you could even update and modify as going forward. So that was kind of my thought. Kind of, you know, if you pin me down today, what the high level lessons of what I've got, I would make one final comment that, again, I think there's a lot of stuff happening in LEO, that low Earth orbits that you might want to think about leveraging. Again, I would recommend, if you haven't already, talked to folks at the Space Development Agency. I think they've got some really cool stuff, similar nature, that would definitely fit some of your needs going forward. And I think you know about some of those, but if you haven't, I would definitely recommend talking to those folks. So if you're interested in learning more about Chirp or other elements of what I've spoken about, there's my contact information. You can also reach out to Dave Robbins. He's our Chief Technology Officer here at Leidos. Dave and I work close together on this stuff. So either one of us, you're more than welcome to contact. So that's what I had for you, Everett.
Well, thanks, John. And I have to tell you, I may have told you previously, but I have a long history with Chirp. Basically, toward the end of its life, when they were trying to keep it going and find a customer, Greg Sullivan, who you may have known at some point in the past, came knocking on my door. I've actually been behind the wall and seen some of the data that came off the system, so I know what it looks like. And I can tell that you've worked behind the wall because your video has been blurred here. So. But thanks for the presentation. I was fascinated with Chirp, you know, when I first found out about it, you know, the capabilities and the possibilities and so forth. So, yeah, I think you bring some really good points to the table here. So thanks for that.
Yeah, so I encourage the community to keep watching the OPIR community. I think there's a lot of leveraging you can do with the DoD and the IC community to really continue that. As they've shifted to LEO, I think there's some great capabilities there to work with. So I appreciate the opportunity, and I look forward to you guys solving all of our wildfire problems out here in California.
Well, John, I'd also point your attention to the chat. Deepak has a question for you. We're a little bit behind schedule, so I'm going to go ahead and move on. But if you'd like to answer that that question in the chat there from D, that'd be great. And let me check here. Let's see. Is Marion Adini on? There she is.
Can you hear me?
I can.
Great.
And as I've told the previous speakers, I'm going to wink out here and I'll come back on with about 2 minutes left. So that just to give you a visual cue that, and I'll advance your slides in the meantime.
Great. Thank you so much. Thank you. Thank you for the opportunity to be here. It's been an incredible 2 days, and this is quite a meeting of minds, I would say. My name is Marion Adney, and I'm the Director of Amazon and Fire Programs at Conservation X Labs. And I'm going to talk to you about a grand challenge that we're developing around fire and traditional and indigenous knowledge. So it's a bit of a different take than some of the previous presentations. Before I start, I just want to give you a little background. I am a fire and landscape ecologist by training, and I've worked in the Amazon for close to 15 years. That's part of what my talk's about today. And I also want to acknowledge before I start that I'm speaking today from the unceded ancestral homelands of the Ramaytush Ohlone people, who are the original inhabitants of the San Francisco Peninsula in the Bay Area in California. Next slide, please. So I don't have to tell this group that the magnitude, intensity, and frequency of fires is changing and increasing across the world. Next slide. And the recent UNEP report earlier this year showed us that fires are burning globally at almost any time in the year. There's a fire burning somewhere in the globe. And in many cases, they are burning in places that have not had a history of natural fire regimes, but have really more of a history of human-caused fire regimes, such as the tropics. Next slide. And we know from science, from indigenous and traditional knowledge itself, from our own community traditions, that this type of traditional and community engagement with fire on the landscape has benefits for both biodiversity, ecosystem function, and also for human aspects of fire. And one of the recommendations of the UNEP report was actually to integrate better indigenous and traditional knowledge in fire management systems. Next slide, please. We are also hearing from indigenous and traditional communities themselves that they have knowledge and history to contribute around the issue of fire in the lands where they live. And I would say this is a opinion piece actually from last year from the New York Times from an indigenous leader in Brazil and a researcher at the Woodwell Climate Research Center, formerly Woods Hole. But we are hearing this type of thing from many places and communities around the world, including here in the United States. Next slide. And we also know that when fire strikes, in many of the places that it hits, communities are in remote, low resource areas and are often on the front lines. Often communities don't have access to information resources or help from government or other agencies. So they really have to face the fire on their own, and this goes for pre-fire, during fires, and also post-fire recovery. Next slide. And finally, we know that fire is changing. Showing smoke from landscape fires, and this smoke covers this area for many months of the year now. Fire is changing because of climate change, because of land use, land cover change, and human dynamics. And one other consequence of this is that traditional fire methods or engagement don't always work in the same way that they have in the past. So this leaves us with a question of how can we take the knowledge and history that communities have for fire management, for managing and living with fire, and combine that with some of the high-tech science and innovation tools, many of which we've seen showcased in these 2 days, to change the way we think about, manage, and live with fire. Next slide. So now I'm going to tell you just a little bit about Conservation X Labs before I answer this question, which is a technology and innovation company. Actually, we're somewhat of a NGO company hybrid that focuses on the use of technology and innovation to address environmental problems and create solutions. Next slide. We work through three main approaches. One is directed innovation, which is in-house technologies that we develop and then roll out and scale. Another important focus of our work is thought leadership, and particularly bringing together many different sectors and many different communities to think together about a problem. And then the third way is open innovation, which I'll talk about today. Next slide. So we use various mechanisms for open innovation, but the one that I'm going to focus on here is prizes and challenges. Prizes and challenges, which NASA, of course, is a master of, are a way to really define and distill a tough problem that you don't necessarily know the solution for and put it out there to the world to ask for solutions. Part of the real power of this model for me is its ability to bring together people and communities that wouldn't otherwise be working together on a problem. It's also a way to really set aspirational goals when we feel really stuck and we don't know how to address something. Next slide. So I want to just quickly give you an example of a challenge that Conservation X Lab, CXL, is running now, which is the Artisanal Mining Grand Challenge in the Amazon. And this is just to make it a little bit more concrete. Artisanal small-scale gold mining is one of the thorniest problems in the Amazon that many people do not know how to address. And I would argue that fire is one of the other thorniest problems in the Amazon and elsewhere. But in this challenge, we distilled the challenge into 3 buckets of safeguarding ecosystems, improving supply chains to make room for responsibly mined gold, and promoting and sustaining formalization or regulation of the sector. And another element that I just want to point out is the Amazon Collab, which is an accelerator model in which we have embedded the 13 finalists of this program to actually partner on the ground and test their innovations in the context. And the prize will be chosen based on how well they do in this 6-month program. Next slide. So to bring it even more home, this is a picture that I took a couple of weeks ago in Peru of a young graduate student from UC Berkeley who has invented a material that can capture gold and mercury without any toxins. And we brought him to Peru. And in this picture, he is meeting with a miner in an extremely remote area in the Peruvian Amazon, and through an interpreter, created a partnership on the spot to test his innovation with this miner. And this, I put this in here because this is just an example of the power of the types of collaborations that can come out of this kind of mechanism. This young, bright young man might not have been interested in working on this particular environmental problem with his invention that could be used in many different applications. Next slide. So this brings me to the Fire Grand Challenge, which is currently under development. We received funding from the Gordon and Betty Moore Foundation for a year-long process to develop this challenge, create a community of stakeholders, and fundraise for the implementation of the challenge. And it's based on the idea that I laid out in my first few slides that traditional and local communities have deep knowledge and practice of fire management, but need new tools and need to join in these types of collaborations with people like you and others to figure out how to get tools implemented on the ground. We have chosen 3 geographies for this challenge, and these 3 geographies, the Amazon, the American West, with a focus on California, and Indonesia, share histories of traditional fire management. They're also widely different, encompass many of the dynamics of fire globally. So one of the hopes is that innovations that are applicable to these contexts can also be scaled for other contexts where fire is an issue. Next slide. And we chose these 3 geographies based on a variety of characteristics, including fire drivers, spatial scale, biodiversity and human impacts, histories of traditional and indigenous burning, as well as funding and partnership networks that are available in these geographies. Next slide. This is just a quick picture to make the point that problem definition across these 3 geographies and with this incredibly complex topic is messy. And this is part of the mapping that we're doing in collaboration with stakeholders to figure out where are the critical leverage points for working through a challenge model. Next slide. And so this design is under construction now, and I'll give you a timeline in a minute to explain the process a little better, but we are working with fire experts, community, indigenous organizations and leaders, innovators, inventors, funders, and many others to really think about in that complex situational analysis, as I call it, or mapping of context, where are the points that a challenge model that focuses on this intersection of indigenous and traditional knowledge with technology can really make a difference. And these are some draft ideas that we have, but certainly not a definitive list or the challenge buckets yet. The challenge buckets being, for example, what I had laid out for the artisanal mining challenge. Those are not yet developed. Next slide. So this is just to give you a little bit better idea about this process. We are currently in, as I said, deep in this design phase, talking with all of these different stakeholders. We will be writing a landscape analysis, which is a document that lays out these contexts and the different potential areas for a challenge and actually uses a set of criteria to decide which are the areas where a challenge model is the best fit. And then we'll be hosting a series of small meetings that we call little thinks, one in each geography in the second half of the year, and a big think to vet and workshop these problems and buckets for the challenge, as well as the challenge design with the people that will be involved in the challenge. And then we hope to launch this challenge in 2023. We are also fundraising for the implementation and running of the challenge. Next slide. So again, we're really in the partnership building phase, and there are many different ways that people and organizations can partner on a challenge, both as technical and, they should say, design partners as well. Partners that really help us to distill this problem and create the challenge mechanism. Partners that can boost the challenge through your networks, through other media, when we actually get to rolling it out, to bring in the applicants across these different communities. When we actually have innovations, we will want scaling partners to start to do things like we have in the collab acceleration model to start to get these innovations tested on the ground, and then of course funding partners as well. We have an email for this. It's fire@conservationxlabs.org, and I would encourage any of you to reach out if you're interested in knowing more or contributing your expertise or in other ways. And next slide. So I'll leave you with this image of an indigenous firefighter in the Xingu region of the Brazilian Amazon, and thank you very much. I was going to say I'm happy to take questions.
Yeah. There we go. Sorry about that. Yeah, that was a great presentation. Thanks so much for that. I don't think David Green is still on. I think he dropped off a little bit ago, but it'd be nice to have some collaboration with David Green on the challenge here. There may be some opportunities for cross-pollination there.
Yes, we're talking.
Oh, good. I'm glad to hear that. Also, Amber Jean McCollum from the Bay Area Environmental Research Institute. says, thanks, Marion, great presentation. Looking forward to hearing more. So yeah, anything we can do to foot stomp your challenge and help to broadcast that out. I'm glad to see that you're involved with the Moore Foundation. They've been doing some really great stuff the last couple of years, and it's a great philanthropic organization. Very interested in the fire challenge, so I'm glad to see that connection there too as well.
Indeed, I actually just came from the Moore Foundation. I was with them for 5 years and just left at the end of this year to come to Conservation X Labs. So I'm quite familiar with the fire portfolio and very excited about it.
Well, thank you. And any other questions for Marion while we have her here on the center stage? I don't see anything in the chat. So we'll go ahead and move on to the next presentation. Thank you again, Marion.
Thank you.
Okay. There we go. Rod, you have 15 minutes and I'll come back on with my camera with roughly 2 minutes to go, and I'll advance your slides in the meantime.
That's great. And just to ensure that my colleagues from Sierra Nevada are also enabled at this time to pitch, correct?
Hey, Rod, Scott, I'm here.
Okay, wonderful. All right, ready to go. So hello, everybody. I'm Rod, the CEO of Rogo Fire, DBA, Rogo Communications. Thank you for your engagement today here with me and with my partners from the Sierra Nevada Corporation. We are here to inform you on the features of a new instantly deployable end-to-end communications and data acquisition solution that we have made for wildland firefighters who operate in remote, austere, and cellular denied areas. I started Rogo Fire in response to the Yarnell Hill tragedy that took the lives of 19 brave Granite Mountain hotshots in 2013. As you likely know, these 19 men burned alive at the scene in Yarnell Hill due solely to a lack of situational awareness and poor communication. When I heard about this news, I was deeply bothered by it. I felt mad, I felt angry, thinking that the same thing could happen to my brother, who is a 30-year wildland firefighter here in Colorado. When I did ask my brother, who has fought in well over 100 wildland fires, how could Yarnell Hill happen? My brother told me, Rod, we're still using paper maps, compasses, and two-way radios. The lack of technology astounded me. Could you imagine if your brother, sister, your daughter, or your son were burned alive in a fire? How would that make you feel? I know how it made me feel. I felt saddened, and then I felt angry. Angry that a better communication solution method didn't exist. And that's why I designed the Rogo Communications solution. Slide 2, please. The agenda for today is providing a description and the features of the Rogo drop block and the operation and scheme of our combined Rogo and Sierra Nevada system with Sierra Nevada's Ronin HAP. HAP stands for High Altitude Platform. Then we'll have a Q&A with everyone. Next slide, please. Rogo's drop blocks are instantly deployable data and communications hubs, which is especially critical during initial attack. The benefit is the ability to instantly communicate with others and access critical scene situational awareness information and data in remote, austere, cellular denied areas. This way, safe, tactically informed decisions can be made. Actionable decisions can be made more quickly. Drop blocks provide Dingle-Act GPS tracking, or GPS tracking, also known as Dingle-Act Resource Tracking, or DART. This benefit lets us know who is located where, and what is going on with the weather and wind in their direction, because drop blocks also send in wind speed, wind direction information over satellite out to other firefighters, to the IMET or the F-band on a fire. This way we can know where people are at, who's in possible danger of burnover, and have the communications ability to warn them to get out of the way. The benefit here obviously is saving firefighters' lives and reducing operational liabilities. Situational awareness is the difference between life and death, between mission success and mission failure. Rogo and Sierra Nevada want to ensure that mission success is achieved every time. Another benefit of the drop block is it can help extinguish fires faster by helping align and coordinate the tactical effort of many wildland firefighters operating in remote, austere areas. Another benefit is saving money. In 2018, NIST put out a study for the 2017 wildfire season. They found that through all federal, state, and municipal agencies, $63 billion was spent in 2017 fighting wildland fires. However, the total economic impact in that 2017 season was $256 billion. Going back to the $63 billion, because that's what was actually spent. If the Rogo Sierra Nevada solution can make wildland firefighting just 5% more efficient, that's $3.15 billion saved. Our system pays for itself overnight. Drop blocks will be miniaturized and soon be also FirstNet Band 14 enabled, as well as LoRa mesh network enabled, so we can make them even more valuable during deployment and especially during initial attack. Initial attack is so critical. That's when the fire growth is usually the greatest, and that's also when the most line of duty deaths occur. So during initial attack, we can control that and provide critical scene situational awareness information. Lastly, we'd like to incorporate NASA's rich Earth data information into our predictive analysis software initiatives. Now, I'll hand this over to my colleague, Scott Erickson of Sierra Nevada.
Hey, thanks, Rod. Good afternoon, and I appreciate your time this afternoon. I'm Scott Peterson, a product line director for Sierra Nevada Corporation. I've been with the company for about 6 years and personally involved with high altitude balloons and the stratospheric effort for the last 5 years. S&C is a prime system integrator and thrives on developing innovative solutions to meet the most demanding customer requirements. In light of my past experience, and based on the inherent desire to solve problems, we have partnered to extend communications, sustain an overhead presence with the end state of enhancing situational awareness from the front line all the way back to a command and control location in areas where communications may be limited or non-existent in support of a fire. I'm sorry, can you advance to slide 1?
Should be up now.
For the con-up, thank you. For the con-up on this slide, on the bottom left, we've developed a trifecta approach. Rogo drop block, utilizing small hand deployable balloons along with larger high altitude balloons, coupled with a UAS to support extended communications via a phased plan of execution. This approach provides the 5 key federal agencies, the Forestry Service, National Park Service, Fish and Wildlife Service, Bureau of Indian Affairs, and the Bureau of Land Management, as well as the most important end user, the firefighter on the ground, with tools to improve the ability to counter forest fires, ultimately reducing loss of life, land, and valuable resources. As the phases of execution show on the bottom left-hand portion of this slide, the initial employment of the Rogo capability begins with a ground-based infiltration via firefighting vehicles upon initial attack. This capability will instantly provide situational awareness, extend communications, and provide key data to counter a fast-moving fire utilizing the Iridium network. Phase 2 involves launching small handheld balloons with an air-launched effect ALE UAS, known as the Ronin, pictured on the right at the 12 o'clock position, being held by an individual. The Ronin will be configured with an onboard Rogo drop block that can be airdropped from the fuselage at a pre-planned location or hand-flown to a location for an airdrop. These small balloons have a shorter duration, between 48 and 72 hours, with an altitude of about 60,000 feet. The small balloons are depicted on the right at 2 o'clock in the pictures. Phase 3 in the concept of operation establishes a mesh network architecture overhead the fire, and provides beyond the horizon communications as well as FMV to a forward location or a rear C2 node. These particular balloons can remain overhead for 30 to 45 days, operating at altitudes between 60 and 75,000 feet. This balloon's pictured on the left at 10 o'clock on the pictures to the right on the right of the slide. The final phase brings all assets into a mesh network, enabling seamless communications between all airborne nodes, ground operators, and C2 locations. Next slide, please. The intended purpose of this slide is just to provide a visual orientation or pictorial of a high altitude balloon launch as it applies to a ground fire and the associated elements involved in fighting the fire. On the left of the slide, the balloon is launched and ascends to altitude, again, roughly 60 to 75,000 feet at 1,000 feet per minute. So it's afloat and ready to operate approximately an hour and a half after launch. The balloon gondola in this scenario is configured with the Ronin UAS that has a ROGO drop lock in the fuselage. The Ronin UAS is released from the balloon and free falls to a predetermined altitude and then begins flying to a release location. Once overhead, the ROGO drop lock is released and recovered on the ground. The high altitude balloons stay overhead and provide the mesh network architecture to pull all associated assets and locations into the communication node for instantaneous information and data sharing. Next slide, please. This slide provides a way ahead for the ROGO drop lock and the high altitude stratospheric balloon capability with the UAS embedded. On behalf of myself and Rod Goosen, I'd like to say thanks for allowing us the time to present this concept. We believe this concept will reduce the loss of life and resources while enhancing situational awareness for all involved in combating forest fires. We look forward to any questions you might have, and more importantly, an opportunity to demonstrate this capability in the vicinity of a prescribed fire or a controlled burn. Thank you.
Well, thanks, Rod and Scott. I don't see any questions in the chat there. Anyone have a question they'd like to ask before we move on to the next presentation? Or any comments for that matter?
Sure, this is Vince. Hi, Rod. Can
Hi,
you
Vince.
rewind back, or Everett, can you rewind back to, I think it's the second slide? Just curious about the drop lock and its setup or radio frequencies.
This one here?
Yeah, I guess that's the one. Okay, so the drop lock is really it's a communications device, or can you explain it a little further to me?
Absolutely. The drop lock is indeed a communications device. Right now, we transmit everything over Iridium satellite. Iridium satellite, it uses the L band, whose signals are very robust in under dense foliage, whether it's deciduous or coniferous trees. So Iridium is much more robust as far as signal strength in the middle of the forest than something like Starlink is. Another thing is that Rogue is the very first private company to figure out how to send long data strings over Iridium satellite short burst data protocol. So we can send a lot of data, a lot more data than a lot more data over Iridium's small pipeline than is ordinarily possible. We also reformat that data into a lightweight packetized format. And by doing this, we're essentially increasing Iridium's bandwidth. So right now we are all Iridium, but as I alluded to on my slide, we are also going to FirstNet Band 14 enable the drop lock. And we're also going to LoRa enable the drop lock so that we can use cellular if that's available, or a mesh network if that's available. But if geographical or obstructions or distance prevent the line of sight communications that both cellular and LoRa need, then we can backhaul everything over satellite to ensure firefighters and other first responders can get the critical scenes information they need in a timely manner.
Good, thank you. So it does also voice, voice communication, just data communication like you're showing?
Right now, we do, right now, we just do data. We
Okay,
are working on sending voice memos over as data files over packetized, as packetized data files over Iridium for point-to-point communications. So
okay,
you can send a pre-recorded message out to a particular individual or group, or to all groups within a geofenced area.
okay, thank you.
Quick question, how do you deal with the high velocity winds associated with firestorms?
Insofar as,
Launching balloons, maintaining balloon tracks, recovery, it sounds like you have this pipeline. How's it work in a 15-mile-an-hour wind?
okay, you're talking about the balloon deployment, correct?
Yes, sir.
Okay, so I'll let Scott from Sierra Nevada answer that.
Yeah, so typically for the balloons, they'd be launched away from the fire and then flown over the fire and then maintain station seeking or keeping over the fire at 70,000 feet. I don't think they're going to be impacted by the weather on the surface or
But I live in the Southwest, and I know that when there's a red flag warning, it covers multiple states. And so if you're trying to launch a balloon from New York, how long does it take to get over Arizona?
I figure they're traveling probably 10 miles per hour.
Wouldn't you just truck it or do something that's at 60 or 70 miles an hour?
Yeah, so we can maximize the jet stream, assuming the jet stream's going in the right direction. In
I'm
theory,
talking in this case, ground transport. If you have a headwind, I know from flying ultralights across the country 6 times, I make record time going from the West Coast to the East Coast, but I have to spend 5 times more time headwinds dealing with that. So I just wondered with a balloon, I worked with airships and wind, yeah, when you get up to the stratosphere, you get out of those influences, but when you're on the ground deploying this for an emergency, how do you deal with 50-mile-an-hour winds day and night? That's what we're dealing with right now at this time of year. I think it's something worth studying is my point. And I admire what you're doing. So I hope you and we can follow up with further discussions.
I think it would be, the ConOps it would be deployed in the vicinity, or, wouldn't be from New York out to Arizona. It would be something
Right.
close by, would not be affected by the local weather pattern associated with the fire.
Right. Well,
Yeah,
it's I admire again what you're doing. I've worked out of Mojave with airships and know that getting them off the ground is a whole different story than what they do at 60,000 feet. So I appreciate again what you're doing and look forward to follow up.
And then also with that, because of Rogo's instantly deployable devices, we can at least get comms and situational awareness on the ground immediately while the balloon gains altitude and or flies around areas of high wind.
Okay.
We're going to have to take this offline, guys. And thanks very much, Rod and Scott. And thanks for presenting here. And we're now going to move on to Yvonne Boos. And Yvonne, I'll go ahead and advance your slides, and I'll bring my camera back on when you have about 2 minutes left.
Great,
Thank you, everyone.
thanks.
Thanks,
Can
Rod.
you hear me?
Yes, we can. You're loud and clear.
Great. So thanks, first of all, for the opportunity to speak here. I'm the last one, I think, for the roundup session and finishing this day. So that's very exciting, and I hope you all are bearing in with me. So a few words about myself. I'm an atmospheric scientist by training. I worked a few years at the German Aerospace Center before joining Brisometer 2 years ago to the science team of Brisometer and being part of the wildfire tracking development in the last 2 years. Not sure if Brisometer is well known amongst this community. So a few words about us. We are a growing startup. We grew recently to about 100 employees. About half of us are in the R&D and the science teams, and we're a group of environmental scientists, atmospheric scientists like myself, remote sensing experts, but also biomedical scientists and several data scientists. And the other big part of the R&D are computer engineers and software developers who make sure that our models are running. We're based in Israel, but we have offices also in the US, Ukraine, and other places in Europe. And the company originally comes from the area of air quality. So the company was founded with the vision to improve the health and the well-being of billions of people around the world by making air quality information accessible and understandable. And but we also soon afterwards started to provide pollen information, just because we see it as another type of air pollutant. And of course, air quality and wildfires are closely related. Wildfire smoke is one of the most harmful air pollutants nearby wildfires, but also, as we know, far, far away from wildfires, as wildfire smoke travels often to very far distances. So I get during and towards the end of the presentation back to the topic of air pollution and of the impact of wildfire smoke, because we're doing this in parallel to the wildfire modeling. But I also see here one of our key strengths is to provide wildfire locations, perimeters, together with their impact on the air quality around them. One last word about what we do with all this data. One second. Yeah. One last word before we move to the next slide about what we do with this data. We provide the wildfire information, the air quality and the pollen information for free in our app and on our website to like all kinds of end users, but we also sell our data for global leading brands. Those are our customers. And some of you might know us from the Apple weather app, where we have our air quality data and also the Apple Maps. Next slide, please. So our wildfire tracking system, the features, so such that you know what we're actually doing there, is that we provide wildfire perimeters for fires larger than 500 acres. That's relatively large, so we're currently working on decreasing this lower limit. We operate globally, so we provide fire perimeters on a global coverage and update our data every hour. We show these fire perimeters accumulated over up to 72 hours, simply for safety reasons, to take smoldering areas into consideration and so on. What we basically do, and I'll get in the next slides to it, we use a fusion of satellite data to get the best basically between being able to detect it as early as possible, but also to refine the shape and the accuracy, so on. And we then also integrated with data from authorities, so from governmental sources in almost 50 countries worldwide. And we use for that, if available, the fire name, for example, the official fire size, if there is a containment forecast date, and so on. We provide this data with our fire perimeters. So basically, how does this wildfire tracking work? So going back to the air quality, there we no, please, once back.
Sorry.
Exactly. Thanks. Good. I'm trying to remember to say next slide. Okay. So from the air quality, which we're working in since 8 years already. Here we have really proven our abilities to integrate data from all kinds of different sources. So what we do today is that we, for the air quality, collect data from about 50,000 sensors worldwide and ingest those into our air quality modeling. Now, we took this knowledge of being able to handle these various data sources of also various quality and availability, and to get the best out of that. And we apply this knowledge now in the wildfire wildfire space, where we also collect data where we can and bring these different layers together. So obviously, geostationary and polar orbiting satellites are the basic, but we also use land cover information, vegetation information, terrain, and so on. We then apply our data filtration models, especially on the remote sensing information, to make sure that what we actually think is a fire pixel is actually one. And then we cluster the data and provide the parameters. And then, as I said, we finally provide these parameters together with the official information from authorities to make sure also our users have that at the same location. And then finally, we provide this data in our app or in our website or through an API for our commercial customers. Next slide, please. So for our false positive filtration, we developed dynamic algorithms that take, amongst others, land cover into consideration to, in addition to the false positive filtration that's already done, to make sure that we're decreasing the rate as much as we can, and yeah, to make sure that what we show as fires are actually fires. Next slide, please. We then also, to improve the accuracy of the fire perimeters, we first, once we have the rough satellite pixels, we do the terrain correction by digital elevation models. And then in the end, once we have the parameters, use land cover information and also terrain information, and also the combination of the various satellite pixels to make sure to locate the fire as exactly as we can within those pixels. Next slide. Something yeah, a bit special, I think, that we do is that we provide our customers with what we call a confidence level. So using machine learning algorithms, we assign each of our fires a confidence level, because of course, even with the best false positive removal algorithms, we're still gonna have some where we are unsure, and therefore we use these this later on, these algorithms later on to give a confidence level both on the existence of a fire perimeter, but also on the exact shape. And we provide these levels to our customers for them to choose, because there are actually different use cases where, of course, for some that go for the safety first direction, that a false negative should not occur at all, and are fine with having maybe a few false positives. But there are actually other use cases that are the other way around, that rather, if a fire is shown, it to 100% should be a fire. So therefore we have this value to let our customers choose on that. Next slide, please. So this is just a small animation of our fire parameters for the bootleg fire. where we see in blue our the pulsometry parameters and in green the NIFC parameters. And I don't know, I hope it only stopped for me, and generally it's still running. Maybe you can go back and forth, because I think it was running before. Yeah, great, thanks. So generally you can see that the parameters agree pretty well, just that the green, so our parameters appear a few hours before the NIFC. So that's one of our ways to make sure that what we're doing is related to reality. And in the last slide, also one more slide, thanks. I'm going back to air quality as I promised. This is how we you can see our air quality information together with our fire information. So in the dark orange, those are the parameters of the Black and the Bear Trap fires, both in New Mexico, still currently burning. And around it, you see the impact on the air quality in purple and then dark red. You see the hazardous and unhealthy air quality categories of the EPA air quality index categories. So these are the two worst categories. And then on the left side, we also provide the concentration of the pollutant that actually causes this very low air quality, in this case, obviously PM2.5, which is because it's wildfire smoke. And we also give advice on how to protect yourself from this pollution. And that's what I have. So if there are questions now or later, I'd be glad to hear from you.
Yeah, that was very nice, Yvonne. I also, while you're talking there, I went to the Play Store to see where the Breezometer app is, and I was able to find it, and so I'm planning on using that now that I know about it. But
Great.
And we did have a discussion earlier. I don't know when you joined, but we were having a discussion earlier about the health impacts, and you know, that there may be more that we can do. So we may be reaching out to you if we pull together some folks to have that discussion.
Yeah, great.
So are there any? Let me check the chat here. Okay. Yeah, I don't see any questions here in the chat. Birgit or Vince?